Okay, this is the P4 paper from October 2023. It's question number 7, and this is a modelling equations question. We're going to be modelling with differential equations at the end. It's integration. We're going to be doing a little bit of partial fractions work in there, but there's a lot of different parts to this question. So let's jump in and get started with it. It says we've got the number of goats on an island. It tells me initially that there's 3,000 goats, but it does also say that x is measured in thousands. So that's telling me t equals 0, x equals 3. And it then says, right, yeah, okay, we're going to model x as being this equation here that's got our k in. X is going to be given by that. And it says, can we work out what k is? Well, yeah, we'll jump straight in because there's a lot of work to do with this one. So part A, it tells me this is the model. K, 9t plus 5 all over 4t plus 3. But then it says at t equals 0, and it doesn't say x is 3,000, it says x is 3 because it's measured in thousands. So don't let that catch you out. They try and do that a couple of times in this question. 3 is equal to k lots of, if t is 0, then we have 0 plus 5 over 0 plus 3 here. So that gives us that 9 is equal to 5k, which gives us that k is equal to 9 over 5, and 9 over 5 works out to be 1.8. So part A done. It then says, hence calculate the long-term population of goats predicted by this model. That's a pretty standard thing that they do with these modelling questions as well. So if we have the situation, well, let's write out our equation again now, but replacing k. X is 1.8 lots of 9t plus 5 all over 4t plus 3. But now we're saying long-term population. So long-term population is as t gets really, really big, and I'm going to take t being or tending to infinity. This is a really nice way of doing it. So x will tend to 1.8 lots of, and we can write this down, 9 infinity plus 5 all over 4 infinity plus 3. This is a nice method if you've not seen it before. So if we're looking at this, if I'm looking at 9 infinity plus 5, well, the 5 doesn't make any difference to 9 lots of infinity, so that's really 9 infinity there. Following the same logic, 4 infinity plus 3 is 4 infinity. And if I get to that situation now, you can cancel these numbers out. So a really clever little trick here that then means that x is equal to 1.8 just multiplied by 9 over 4. And so that tends towards 4.05. But again, as we'd said previously, don't get caught out. It's 4,050 then in terms of the actual number of goats. So x tends towards 4,050. Then we go on for part C. It says, right, yeah, we've got a new model that we're going to be using, this one here. And before we do any work on it, it says, can you just quickly work out that by partial fractions? Well, absolutely we can. It should be something you practice lots and lots and lots. Let's just chase straight through that one. So 3 over x, 9 minus 2x. If I'm going to do partial fractions, then the partial fractions are going to be in that format there. A over x, b over 9 minus 2x. If we're going to do our partial fractions on that, then I'm hesitating because it's so straightforward, but I just want to make sure that I do all the steps each time. This is going to be a 9 minus 2x plus b x all over x 9 minus 2x. I'm hoping that's not causing you any problems at all there. Let's just go through the process, same as always. So I would equate the numerators at this stage, which means that I get 3 is equal to a 9 minus 2x plus b x, and then I just want to get rid of the a and the b separately, don't I? So if I choose x equals 0, I'm going to get 3 is equal to, is equal to a times 9, and plus that part there will be 0. So that gives me that a works out to be equal to a third. And now what do I choose to get rid of the a this time? I'm going to have to choose 9 over 2, aren't I? So that then that A part will disappear. We'll get 3 is equal to 0 here, plus 9 over 2b there. So that means that b will work out to be equal to 2/3. So if I have that situation, then my original fraction, 3 over x, 9 minus 2x, is equal to a, that was 1/3 over x, plus b, that was 2/3 over 9 minus 2x. And let's just tidy that up. Let's just make that look a little bit more reasonable. That would be 1 over 3x, and it would be 2 over 3, 9 minus 2x there as the partial fraction. So, big question, isn't it? We've done part C. Part D then says, can we solve the differential equation with the initial condition, so with t equals 0, x equals 3, to show this thing here? Well, yeah, hopefully that will just come out from actually doing it. What they're really saying is, can I solve the differential equation? And I can certainly have a good go at doing that. So for part D, if I'm trying to solve the differential equation was 3 dx by dt is equal to x 9 minus 2x. We're going to separate out the variables. The x's, the t's are going to come up there, and the x's are going to go down there. Separate those out. So I'm going to end up with 3 dx all over x 9 minus 2x is going to be equal to the dt coming up here. And it's not a surprise that our part C here is absolutely right there as well. So I'm going to replace that with the partial fraction in a moment. But before we do that, so we would then say the integral of that is equal to the integral of that. So I've got not the integral of 3 over x, I'm going to change it to my partial fraction, the integral of 1 over 3x plus 2 over 3 9 minus 2x dx is equal to the integral of dt. I just think it's simpler to take a third out here. So at this stage, I'm still not integrating yet. I'm just going to take a third out of both terms there, which gives me 2 over 9 minus 2x dx is equal to the integral of dt. And now looking at the left-hand side here, you should be able to integrate both of those pretty quickly. I'm not going to spend any time doing it. If you need to go back and do some revision of integration, then do that. But this left-hand side, the integral of 1 over x is log x. The other one's slightly more complicated, but still really not that hard. The integral of 1 over 9 minus 2x would be log 9 minus 2x, but then because of the minus 2, it becomes minus a half, doesn't it? We're dividing by minus 2, okay? Then the fact that I've got the 2 up here as well means that actually becomes 2 over 2. And then the integral of the left-hand side will become t, right-hand side, sorry, will become t plus c here. And then they said, right, for the initial conditions. So the initial conditions were at t equals 0, x was equal to 3. So we can use those to work out what c is. I could combine those two logs together. The only reason I'm not going to is I know it drops out really quickly. Here on this left-hand side, I get log 3 minus log 3. So because I get that, obviously we don't need to worry about the 2 over 2, that's just going to cancel out. That's going to be 0 anyway, is equal to 0 plus c, so c works out to be equal to 0 anyway when I'm looking at my answer here. So my answer now becomes 1/3 log x minus log 9 minus 2x is equal to t. And what they asked us to do, a long way up, isn't it, is to get x equals that. And you just think, okay, well, what I've got to do then is I've just got to rearrange and make x the subject of the formula here. Not going to be too complicated. We will use the log rules that I could have used a little while ago, but now here I'm going to say that's log x over 9 minus 2x, just using our log a minus log b is log a over b. Let's multiply everything by 3, so I get log x over 9 minus 2x is equal to 3t. And now here at this stage, I'm going to now e both sides. I wanted to get to a stage where I just have a single log something, log of a function is equal to, and then I can e both sides, which I'm going to do. I'm going to get x over 9 minus 2x is equal to e to the 3t. And I've just got to patiently now rearrange this to get x the subject. So let's multiply everything by 9 minus 2x is equal to e to the 3t. I know what I've got to do. I've got to multiply out that bracket then. Really slowly, just take your time when you're doing this. Minus 2x e to the 3t. The whole point being I can now take this x over to the other side. So I've got x plus 2x e to the 3t equals 9e to the 3t. Take x out as a factor. 1 plus 2e to the 3t is equal to 9e to the 3t, which is then going to give me my answer. X is 9e to the 3t all over 1 plus, I'm just going to slightly write that differently, 2e to the 3t plus 1. And if we go back, we're not quite there, we're almost there with our answer. We notice that there's no e to the 3t on the top there, and there's an e to the minus 3t on the bottom there. That's no problem at all. If we look at our function, wherever our one is, and just divide everything by e to the 3t, divide the numerator and the denominator by e to the 3t, then the answer does drop out. So here we get 9 over 2 plus 1 over e to the 3t, which is e to the minus 3t. So then we get the actual function that we were trying to get there. Part E, I'm not going to keep going up and down scrolling here, but part E says what happens as t tends towards infinity. Again, it's exactly the same, exactly the same skill as we used earlier on here. What happens as e tends towards infinity? So we get x equals 9 over 2 plus e to the minus infinity. How am I going to get rid of e to the minus infinity? No problem at all. Sorry, tends towards there. Let's call it, do that properly. As x will tend towards that. What does e to the minus x look like? E to the minus x looks like that. So if we're over here, as t tends towards infinity, e to the minus infinity is just going to tend towards 0. So x tends towards 9 over 2 plus 0. So x tends towards 9 over 2, which is same idea again. There's repeating lots of parts of this question. Not 4.5, but 4,500 goats if we were answering that. That's worth 1 mark, that last part. So I've given you a lot more detail than you needed to for that. Yeah, really long question. But lots of the same skills being repeated and relatively standard with some of those, some of those little ideas you need to be aware of. So that's a really useful one for you to have a look at. Hopefully that all makes sense to you.